Up to this point, we've only been dealing with DC circuits, direct current circuits, which means the potential was constant. The current was constant, nothing was changing. As soon as the circuit was hooked up, it very quickly came to a steady state and the current didn't change. Now we want to start to think about AC circuits, alternating current circuits, where the potential difference flips and the current starts to build up in one direction through the circuit. The potential difference flips and the current goes in the other direction through the circuit, and it goes back and forth, and it's constantly changing. It's always changing. So before we get into that, let's look at a simpler case. We're going to ease ourselves into thinking about things that happen in AC circuits, but we're going to do it by looking at DC circuits with a switch. And what happens the instant we close the switch? What happens after the switch has been closed for a long time? Well, then it's just a DC circuit. And what happens the instant we open the switch? So we're looking at those cases where we get sudden changes in the current. And then that'll help us think about what happens when we have a more gradual change in the current in an AC circuit. Here I have a very simple DC circuit, a battery and a resistor and a switch. So the first thing we're going to do is close the switch, and we'll walk through what happens in detail. As soon as we close the switch, current begins to flow in this circuit in this direction. This current fills the space around it with a magnetic field. If we're on the interior of this loop of wire, the magnetic field will point into the page. A loop of wire with a changing magnetic flux feels an induced EMF. And that's what we have here. We have a loop of wire. As soon as the current started to flow, a magnetic flux increased into the page. There was no magnetic flux there at first. Now there's a magnetic flux into the page. And so that induces an EMF in this loop. And what direction is that? It's in the opposite direction. It's trying to push a current in a direction that would reduce the flux back to zero. It's trying to push a current in the counterclockwise direction. Because it's fighting us, because it's pushing against the current we're trying to drive through the circuit, it's called a back EMF. It's a potential that's pushing current opposite what the battery is trying to do. Another term we have for this back EMF is self-induction. Self-induction because the circuit itself is creating this. So this is an electromagnetic induction effect, but it's created by the circuit itself. So we say it's self-induced EMF or self-induction. The electromagnetic induction that creates this back EMF is created by the circuit itself. So let's see if we can figure out what it is. We know from Faraday's law that the EMF generated is minus N d flux dt, the change in magnetic flux per time. Since we're talking about the circuit itself, the self-induced EMF, we put a little subscript here. The L is a symbol we use for inductance. Let's take a look at what happens for a solenoid. It will become clear in a minute why we're using a solenoid. But in a solenoid, an ideal solenoid, we can calculate the magnetic field. Since the magnetic field is constant over the area in an ideal solenoid, we just get B times A for the flux. We can combine those. And we can see the only thing changing in time was the current. If we multiply by I over I, we don't change this value at all. And then we can write the numerator in terms of the flux. And we call this the inductance. This is only true for an ideal solenoid. But for an ideal solenoid, we get the inductance. L is the number of turns times the magnetic flux over the current. The units for inductance are the Henry, and 1 Henry is a volt second over an amp. Let's think about what this effect is doing to the circuit. We have a circuit here. We close the switch. The way we've been thinking about this up till now, that current instantaneously goes to its maximum value and just stays there. This is telling us that we close that switch, the battery tries to push the current, but there's this back EMF that tries to push back, and at that instant, what happens? Nothing. The current from the battery is trying to go this way, the current from the back EMF is trying to go this way, and we have a stalemate. We have no current at that instant. But the battery keeps trying to push, and the rate of change of the flux is going down. It's not changing as abruptly as it was when you first closed the switch. So the back EMF gets smaller and smaller. And what happens if we were to plot the current as a function of time, at the instant we close that switch, there'd be no current because the battery's pushing in one direction and the back EMF pushes hard in the other direction, and we get no current at that instant. But the battery always pushes with the same amount, and the back EMF diminishes as time goes on because things aren't changing as abruptly. It all has to do with the rate of change. So as time goes on, this current approaches its maximum value. Sometimes this is desirable. Sometimes this is an effect that we want in our circuits. Some people say it makes the circuit sluggish. It makes it slow to respond. And that might be an effect that you want in a circuit. And so how would we magnify it? How would we put something into our circuit that would intensify this effect? Well, we could put a solenoid into our circuit, because a solenoid has lots and lots of turns of wire right next to each other. So this effect I'm showing you here is for just one turn, because my loop I drew had one turn. But if I had lots of turns, this effect would really be magnified. The extra coils would make this a much stronger effect. So if we were trying to produce this effect, what would we put in our circuit? A solenoid. So if we're using a solenoid in this capacity, we don't call it a solenoid anymore. We call it an inductor. The symbol looks like a coil of wire, like a solenoid, because a lot of inductors, that's what they are. They don't have to be a coil of wire, but a lot of them are.